So we are extremely excited about this new technology, and here to give you a little bit more detail and insight about 3D V-NAND technology, I would like to introduce our next speaker, Dr. Kye Hyun Kyung, who's SVP and the Flash Design Team Leader. So please welcome Dr. Kyung.
Hi, good afternoon. My name is Kye Hyun Kyung, and I'm leading the Flash Design Team in Samsung Electronics. Last year, as Jim said, Samsung started mass production of 3D V-NAND for the first time in the world. And recently, we have successfully developed the second generation of V-NAND, suitable for SSD. Today, I'm very proud to introduce to you our new innovative 3D V-NAND technology. Can you guess what this is? This is our 1x nanometer 128 gigabit 3D MLC device. Inside this chip, there are 4.3 billion cells, enough to 43 billion cells, enough to store 16 gigabytes of data. If we expand this tiny area, we can see this line of cells, a so-called string above and flashing. Why don't you take a closer look? This image shows an example of Samsung's 1x nanometer NAND flash memory cells. When designing those NAND flash cells, our mission is to shrink the size of them so that we can fit more cells into less space. That way, we can produce NAND flash memory with more and more capacity. This figure shows the history of NAND flash memory cells. In 1999 is very important because the first storage with the NAND flash is equipped for IT device. Back to then, the design node was 120 nanometer. Through shrink technology, we have been able to reduce the design node down to the 10 nanometer class. The benefit of reducing cell size are vast. In 1999, with the 120 nanometer technology, we could only produce chips up to 1 gigabit. But now, with the 10 nanometer class design node, we can fit 64 times more cells in that same area to store 64 gigabit of data. Every time we shrink our cells smaller, we already face technical challenges. First, we need to develop design technology to prevent cell-to-cell interference. And then we should find the right light source for photolithography process. Okay, let me explain a bit about cell-to-cell interference first. Cell-to-cell interference is when the state in a cell can affect the behavior of the adjacent cells because of a coupling effect. Generally, when the cells have a design node of 30 nanometer or more, cell-to-cell interference can be easily controlled by design efforts. However, as the design node becomes smaller, like 1x nanometer, the probability of data corruption due to cell-to-cell interference drastically increases. Put simply, if you think of a cell as your house, the narrower the space between your house and your neighbors, the more likely it is that you will be irritated from hearing all the noise your neighbors make. In this case, just as you would probably invest more money in installing soundproof walls, we need to put money into developing corresponding technologies to solve the problem of cell-to-cell interference. Another task when shrinking is to find the right light source for photolithography used in patterning. This figure shows the fabrication process of a semiconductor device. After applying photoresist to the wafer, the next step is patterning the circuits with an appropriate mask. As the design is lowered, the pattern on the photomask shrink as well. The lasers for the 40 nanometer class design node can be used to inscribe the photomask pattern on the wafer without any issues. However, these lasers cannot penetrate the smaller pattern for the 1x nanometer class design node. So, we need to develop a lasers with a shorter wavelength for 1x nanometer class pattern. The issue is the new equipment for 1x nanometer patterning requires huge investment. Thus, we try to find an alternative solution to overcome these two obstacles that I described. And we were finally able to develop the world's first so-called 3D V-NAND. Thank you. Our research and development team thought long and hard about how to create a circular interference-free structure for more capacity even with larger design nodes. It turns out the answer was very intuitive. We adopted the concept of a layer instead of a nanometer, and we found a way to layer the cells on top of one another. This is called 3D V-NAND. The V in V-NAND stands for vertical, and the name implies this is a three-dimensional structure. The idea of 3D planar NAND versus 3D V-NAND is similar to living in houses versus apartment buildings. If you want to increase the number of houses on one row, you'd have to build the house smaller, right? It's just like increasing the number of cells in 3D planar NAND. On the other hand, in case of apartment buildings, if we want more houses in the same area, we just need to add another floor without worrying about reducing the size of each apartment. This is what 3D V-NAND is all about. Alright, now so far, I described the basic concept of V-NAND. It is simple, isn't it? However, there is no free lunch. Some challenges are present when trying to design 3D V-NAND. To overcome them, three types of disruptive innovation are needed. These are material innovation, structural innovation, and integration innovation. These are completely different from the one used in planar NAND, but once they are developed, they lead to birth of 3D V-NAND. Let's start with the material innovation. Taking the example from before, when building a house, the main material you usually need is wood. However, to build a high-rise apartment, you need reinforced steel and cement. Just like that, the materials used in 2D NAND and 3D V-NAND are completely different. Instead of using conductors, V-NAND requires insulators, while conductors are similar to liquids and charge can move freely inside of them. Insulators are like solid and charges cannot move very well. Samsung has been researching DCTF or charge-trap flashing technology for a long time, and we were able to acquire technology to commercialize it. Next, let's talk about structural innovation. What is the most obvious structural difference between these two, house and apartment? The answer is elevator. To move between floors, you must have an elevator, and the comfort of an apartment residence changes depending on how the elevator is installed. Similar to a rod connecting houses, a silicon substrate serves as a path between cells in 2D NAND. Likewise, just an elevator allows people to move between floors. A channel hole connects layers in 3D V-NAND. The image on the left side of the screen is the structure of a planar CTF NAND. The structure of 3D V-NAND is completely different from 2D NAND, as you can see from the right image on the screen. The structure makes it possible to arrange cells vertically. One thing you should remember is the storage. Storage insulator is covered by a control gate. The third innovation is integration. After developing the structural technology in 2008, we achieved A-layer stack in 2011. And 2 years later, we developed a commercialized 24-layer 3D V-NAND. Finally, we began mass production of a 32-layer V-NAND this year. Right now, I describe 3 innovation technology to make V-NAND. Then, does this 3D V-NAND provide a solution to shrinking problems? In 3D V-NAND, as I said before, because the control gate covers the cell, there will be no interference structurally. In other words, just like a soundproof wall that prevents noise, there will be no cell-to-cell interference. As I mentioned before, shrinking needs a sophisticated light source. But for V-NAND, we don't need it. The reason is the design rule of V-NAND is several times larger than planar. For example, take one piece from the array, in this case, 1/24, and make it 6 times larger, and stack it layer by layer. That's it. The left side and right side has the same density of 120 gigabit. But designer of flash NAND, the 3D V-NAND is 6 times larger. With innovation in 3D V-NAND technology, we could overcome the obstacle caused by 2D planar NAND. And we can even see some excellent benefit from V-NAND. One of the clearest improvement is the increasing capacity. With 2D NAND, even if we keep shrinking the chip to 1x, 1i, or 1z, it will be difficult to break past the 128 gigabit capacity that we enjoy today. However, we believe that we can develop V-NAND flash up to 1 terabit or more capacity with the 3D V-NAND technology. In other words, the maximum bit density of planar NAND can reach only the minimum of 3D V-NAND, even though the design rule of planar NAND touches the theoretical limits. Next is speed. By improving speed, with 3D V-NAND will enhance people's lives. As I said before, we need to develop very precise program algorithm to prevent data corruption due to cell-to-cell interference in 3D planar NAND for smaller design rules. It means for less than 1x nanometer technologies, the data is written carefully using multiple write algorithms in order to avoid interference. As you can imagine, this takes some time. However, in 3D V-NAND, since cell-to-cell interference is almost free, we need only a simple algorithm to write data. Thanks to this, we can get approximately 2x faster write speed. Next, you can experience more endurance with 3D V-NAND. Endurance means how many times you can write to a given cell. The endurance characteristic very dependent on electric field. Because of material and structural difference, the electric field for V-NAND is lower than planar NAND. This means that the V-NAND gets less stress than planar, which results in the lower endurance of V-NAND. Finally, 3D V-NAND leads to more power efficiency. Since the program algorithm for V-NAND has fewer steps, this saves on power consumption. As a result, we can consume just only 54% of energy consumption So 3D V-NAND achieves almost twice the power efficiency. So far, I described the concept of 3D V-NAND. Just change the material and structure, and you get 3D V-NAND, pretty simple, right? But why is Samsung the only company that can mass produce 3D V-NAND? It's because there were a lot of complications we faced when developing it. To explain the challenges, I will show you this figure again. We first obtained the CTF technology in 2006. After 2 years of investment in 2008, we developed the basic structure. After that, we devoted another 3 years and developed just 8 layers of technology in 2011. Then we spent another 2 more years and created the first commercialized 3D V-NAND in 2013. There is a lot of technology involved in this process. Today, I will explain the key process to you now. There is channel hole technology. Do you remember the biggest difference between apartment and the house that we talked about earlier? It was the elevator. Similar to elevators in apartment buildings, 3D V-NAND has changed channel holes. The right figure shows the top view of 3D V-NAND. You can see a lot of holes there. Then let's look at cross-sectional view of the channel holes. We can see that the channel is formed evenly from top to bottom. This is done through an etching process that requires very elaborate control and is a result of intense investment over many years. As the number of layers grows, the process becomes more and more difficult. It's the same concept of building elevators. It's much easier to build an elevator in a small apartment building like that. But how about this tall skyscraper? So far, I described the basic concept. Okay. But even more than this, a more important factor is how many elevators there are. Can you guess how many holes we need in 128 gigabit 3D V-NAND? We need to etch 50,000 holes evenly lengthwise and widthwise in one chip. That makes a total number of 2.5 billion holes for 128 gigabit V-NAND. So how big is this chip? The chip is about the size of your fingernail. Think about it, 2.5 billion holes in your fingernail. Okay, then, how will this 3D V-NAND be used in the future, and what role will it play in the industry? Nowadays, the IT world is changing from computing-centric to data-centric. And I believe that 3D V-NAND will be the ultimate solution for storage in data-centric world. Also, I believe 3D V-NAND can support the storage requirement for the data-centric world, so with more capacity, more speed, more endurance, and more power efficiency. It means 3D V-NAND will be the gateway to the upcoming terabyte era. Thank you for listening to my presentation. It has been my pleasure to show you how Samsung can enrich your lives with its innovative 3D V-NAND technology. Join Samsung and ride the elevator to new heights of innovation in the terabyte era. Thank you.